Okay, this is an example of a proportional turn. This, what I'm holding in my hand, is the inertial sensor. And if we hit run on the program, right now the sensor is calibrating, and then we enter a loop where the motor runs until we make a turn of 180 degrees. So to illustrate that, I'm going to turn the gyro or the inertial sensor to the right 180. And you can see I have a heading printed out of 180. And you see the motor comes to an almost complete stop there. And if I turn it back to the heading of 0, it speeds up. So slow down, speed up, slow down. So as I approach the heading, my motor is going slower and slower, which is going to allow us to make more precise turns and hit the headings that we want to hit. Okay, this is the code for my proportional turns. First, make sure that you have at least a motor to test this and your inertial sensor set up on port 6, so it's called inertial 6. And as I enter the program, the first thing I'm going to do is calibrate that inertial sensor. And while it's calibrating, we're then going to wait for 100 milliseconds to just let it complete. We've got a couple variable declarations here. They're all floats. Recall that floats are variables that can have decimals. And I've got something called actual heading, which will go get the current heading off the inertial sensor. Target heading, which would be the heading the user inputs. I want the robot to turn until this number of degrees. Another variable called error, which is the difference between the target heading and the actual heading. And this will allow the user to basically understand how far away they are from reaching their desired degree. And lastly, I've got a motor speed variable where I just do 0.5 times whatever this error is. And 0.5 seemed to work. You can change 0.5, make it 0.4, 0.6. It really depends on how big of a differential, like what's the max differential that you're going to be working with here. So 0.5 worked for me. Next, so we enter this while true loop, and I'm going to be constantly calculating that actual heading because that's going to be changing as I make the turn. And therefore, I'll also be constantly calculating what that error is because that's also going to be changing, which is also going to change my motor speed. And I've added in here for motor speed because sometimes you can get negative values for error, which would then be reversing your motor going the other way. And that's not what I want to do here. So I'm going to just take the absolute value of that error, and that'll prevent the motor from like switching from clockwise to counterclockwise or vice versa. And we're going to spin the motor forward at that motor speed, whatever that calculated speed is. So as our target heading and our actual heading get smaller and smaller in difference, then 0.5 times that error will, or that number we call error, will get smaller and smaller, and our motor speed will get smaller and smaller. And that's how this works. So as we approach the actual heading, the error value gets less, and therefore the motor speed gets less, and then the speed at which we're spinning the motor gets less. Here I'm just printing out what the error is, and I'm also printing out what the heading on the inertial sensor is as well.